This is the epicenter of a $100 billion industrial revolution. The Micron Mega Fab in New York, the most expensive construction on Earth. Spanning 1.4 million square feet, this is a fortress of silicon engineered to redefine the absolute boundaries of physical limits. The scale is staggering. Imagine 40 football fields integrated into a single class, one clean room, where air purity is maintained at 99.9999%. Every single structural component, over 50,000 tons of steel, is being assembled with the precision of a Swiss watch on a gigascale. Each pillar is anchored into a specialized vibration control slab designed to neutralize the slightest seismic interference from miles away. In the realm of subatomic manufacturing, a single dust particle is a weapon of mass destruction. Here, air filtration is the first line of defense. This investment represents a tectonic shift in global supply chains, anchoring the future of AI and memory manufacturing in the heart of North America. To comprehend the complexity, we must enter the clean room heart, a pressurized vacuum environment where logic gates are carved by light. A single fabrication unit costs $15 billion, a staggering figure that exceeds the annual GDP of entire nations. Deep within these halls, ASML's extreme ultraviolet lithography systems use light wavelengths of precisely 13.5 nanometers. The mirrors inside these machines are so flat that if expanded to the size of the Atlantic, the highest wave would be just 1 millimeter tall. It begins with a raw silicon ingot, purified to 9 nines. This is the ultimate material, the very foundation of the digital age. Diamond wire saws slice these ingots into wafers thinner than hair, capable of carrying tens of trillions of electrical connections. Logistics here is an engineering nightmare. Thousands of specialized tools arrive in climate-controlled vaults from across the globe. With dedicated networks for ultra-pure water and high-purity gases, this is more than a factory. It is a city built exclusively for machines. Behind these seamless walls lies the most sterile environment ever created by man, the Class 1 cleanroom. To maintain this purity, the air is recycled every 6 seconds, filtered through a massive matrix of ULPA membranes. Even the workers' bunny suits are engineered with conductive carbon fibers to prevent static discharge that could fry a circuit. But air is only half the battle. A single chip fabrication requires millions of gallons of ultra-pure water, or UPW. This water is so clean it is technically a solvent. It would leach minerals directly from your bones if you drank it. The UPW plant at Micron is a multi-story industrial labyrinth, stripping every ion and bacteria from the local supply. Every pipe in this system is made of high-purity PVDF, welded with infrared technology to ensure zero interior beads. Parallel to the water lines are the gas delivery systems, pumping high-purity nitrogen, argon, and hazardous silane gases. These gases are stored in massive, blast-proof bunkers, monitored by thousands of sensors with millisecond response times. The electrical grid required to power this facility could sustain a mid-sized city delivered through dedicated substations. In the event of a power flicker, thousands of flywheels and UPS systems engage instantly to prevent a billion-dollar loss. The manufacturing floor itself is a vibration-isolated island floating on massive hydraulic dampers. This ensures that the movement of a truck outside never disturbs the atomic-scale etching taking place inside. Above the cleanroom, a secondary level known as the plenum manages the immense pressure and air distribution. The sub-fab houses the pumps, scrubbers, and power transformers that keep the tools breathing. At the center of this technological storm is the lithography bay, where light becomes the architect of matter. Here, ASML tools worth hundreds of millions of dollars use extreme ultraviolet light to etch patterns on silicon. The process is repeated dozens of times, layering transistors so small they are measured in the width of a few atoms. Connecting these layers is the AMHS, the Automated Material Handling System, a sky-high railway for chips. Overhead robots, or hoists, travel at high speeds carrying pods known as FOUPs, each filled with 25 wafers. This robotic army never sleeps, guided by a central AI that optimizes every second of the manufacturing flow. Each FOUP is its own mobile cleanroom, pressurized with nitrogen to prevent any oxidation of the delicate circuits. As the wafers move to the etch phase, specialized plasma clouds strip away unwanted material with surgical precision. The deposition tools then add atomic layers of conductive metals, building the vertical skyscrapers of the chip. Chemical mechanical polishing, or CMP, then grinds the surface flat to a tolerance of a single nanometer. This cycle, etch, deposit, polish, is performed hundreds of times over several months for a single wafer. Metrology stations then scan the surface using electron beams, looking for defects invisible to the human eye. A single error in the nanometer range can render an entire batch of thousands of chips completely useless. To prevent this, the tools are isolated from the building's shell, sitting on dedicated pedestals of massive concrete. This is the absolute frontier of engineering, where human ambition meets the fundamental laws of physics. Supporting this atomic dance is an industrial lung system, the massive HVAC infrastructure of the megafab. To prevent overheating, a dedicated chilled water loop circulates cold energy equivalent to 10,000 residential air conditioners. Massive cooling towers on the roof exchange heat with the atmosphere, creating a constant plume of industrial steam. Beneath the floors, a labyrinth of acid waste neutralization tanks treats every drop of chemical byproduct before disposal. Specialized scrubbers use high-temperature flames to destroy hazardous gases used in the etching process. Safety is absolute. If a single sensor detects a leak, the entire bay is sealed within 300 milliseconds. Maintenance of these tools is a surgical operation. Technicians in bunny suits perform tasks with calibrated torque tools. Every screw, every gasket is tracked by a digital twin, predicting failure before it even occurs. The gigafab also houses a dedicated power substation, drawing enough energy to power 200,000 homes. Redundancy is built into every wire. 3 independent paths ensure the factory never loses its heartbeat. In the chemical storage wing, robotic arms handle canisters of volatile precursors with zero human intervention. These chemicals are so reactive they ignite on contact with air. They are the blood of the semiconductor machine. The logistics of these materials requires a specialized fleet of temperature-controlled trucks and secure docks. Back in the clean room, constant particle monitoring ensures that the Class 1 standard is never breached. This is a balance of brute industrial power and microscopic delicacy, a feat of modern engineering. The integration of these systems is managed by an industrial neural network, processing petabytes of sensor data every hour. From the humidity in the air to the chemical concentration in the etch tanks, everything is tuned to an absolute constant. This level of control allows Micron to produce memory chips with vertical stacks exceeding 200 layers. Each layer must align with the one below it with a tolerance of less than 1/10 of a nanometer. To visualize this, it is like stacking thousands of sheets of paper until they reach the moon, without a single sheet being out of place. The heat management within these stacks is handled by microscopic cooling channels carved directly into the silicon. As we move toward the back end of the factory, the finished wafers are prepared for the dicing process. High-speed lasers or diamond saws cut the wafer into individual dies, each one a masterpiece of human ingenuity. The sheer density of this operation is what makes the $100 billion price tag a necessary investment.
We are inside the new wafer fab facility, where these autonomous pods are revolutionizing how microchips are manufactured.
Every AI model, every high-performance server, and every smartphone on the planet will soon rely on the chips born in this very room. The challenge is constant. The laws of physics dictate that as we go smaller, heat and quantum tunneling become our greatest enemies. To combat this, Micron engineers utilize new materials like high-K dielectrics and specialized cobalt wiring. These materials are deposited atom by atom in a vacuum environment more empty than the space between stars. The cluster tools that perform this work are modular marvels, allowing for rapid upgrades as technology evolves. Precision is nothing without verification. This is the metrology wing, where electron beams replace human eyes. CDSEM tools measure critical dimensions with a resolution of 0.05 nanometers finer than a single atom. Every wafer is a data goldmine. Billions of measurement points are analyzed in real time to adjust upstream lithography. If a tool drifts by the width of a virus, the system automatically recalibrates the entire production line. Once verified, the dies move to advanced packaging, the secret sauce of modern high-bandwidth memory. Here, chips are stacked vertically, using TSV technology through silicon vias, creating a 3D data skyscraper. These vertical connections are formed by copper pillars, smaller than a grain of pollen, yet carrying terabits of data. The bonding process happens in an inert nitrogen environment to prevent even a single atom of oxygen from causing rust. Specialized underfill materials are injected at the micron scale to protect the delicate stack from thermal expansion. This 3D stacking reduces the distance data travels, slashing power consumption and boosting AI processing speeds. Every finished HBM module undergoes a burn-in test, subjected to extreme heat and voltage to simulate years of use. Only those that survive this industrial gauntlet are cleared for shipment to global data centers. The final product is a masterpiece of density, 12 or 16 layers of memory, working as a single unified brain. Back at the loading docks, robotic sorters pack these modules into specialized anti-static, shock-proof containers. The journey from a raw silicon ingot to this finished AI engine takes over 4 months of continuous precision. Maintaining this atomic-scale operation requires an electrical infrastructure equivalent to a nuclear-powered city. Micron's dedicated substations transform high-voltage power through massive copper busbars, humming with 200 megawatts of energy. In the chip world, a power dip of even 10 milliseconds is catastrophic. To counter this, the facility uses kinetic energy storage. Giant flywheels spinning in a vacuum provide instantaneous bridge power, ensuring the lithography tools never skip a beat. Parallel to power is the thermal management. The fab's cooling loop circulates water chilled to exactly 4 degrees Celsius. Massive centrifugal chillers, each the size of a locomotive, work in redundant arrays to fight the immense heat of plasma etching. But even more critical is the air. The plenum space above the cleanroom acts as a giant pressurized lung. Thousands of fan filter units create a laminar flow, pushing air downward at a constant velocity to sweep away particles. Safety systems monitor every cubic centimeter for hazardous gas leaks, using infrared spectrometers for light speed detection. If a leak is detected, localized scrubbers activate, using thermal oxidation to neutralize chemicals before they exit the building. The fire suppression system doesn't use water in the cleanroom. It uses inert gases to starve fire without damaging the tools. This is a life support system for machines, built with a redundancy level of N+2 for every critical component. Maintenance crews use augmented reality headsets to see through walls, tracking the flow of chemicals in real time. Every valve, every sensor, and every pump is a node in a massive industrial IoT network, predicting its own wear and tear. The complexity is hidden behind seamless white panels, but the engineering beneath is a masterpiece of industrial logic. At the final stage of the cleanroom journey, the finished wafers are moved to the automated die sort area. Here, thousands of microscopic probes touch every single chip to verify its electrical performance at extreme speeds. Wafers that pass are then mapped digitally, marking the exact coordinates of every functional memory die. The dicing process then begins, where diamond-coated blades or thermal lasers separate the silicon into individual units. This is followed by advanced packaging, where chips are stacked and bonded using specialized micro bumps. Micron's HBM3E technology stacks up to 12 layers of DRAM, interconnected by thousands of through-silicon vias. This vertical architecture is what allows AI processors to access data at speeds exceeding 1 terabyte per second. The finished modules are encapsulated in a specialized resin to protect them from moisture and physical impact. Every module is laser-etched with a unique ID, allowing for full traceability back to the specific raw silicon batch. Outside the cleanroom, the outbound logistics center operates with 100% autonomous mobile robots. These robots navigate through the warehouse, sorting and packing memory modules into climate-controlled shipping crates. The crates are loaded into specialized trucks equipped with active suspension to prevent any microfractures during transport. This facility is more than a factory. It is a vital node in the global digital infrastructure, a fountain of high-tech intelligence. The scale of investment, $100 billion, is the price of entry into the future of human computation. From raw sand to the world's most advanced AI memory, the journey of 4 months is finally complete.